Far below the sunlit waves, seawater approaches an icy threshold, yet remains restlessly liquid. If you descended beside it, warmth would vanish long before the ocean became solid. The mystery begins where summer sunlight loses authority and ancient cold water fills the darkness. Temperatures near the abyss commonly hover only a few degrees above seawater's freezing point. Yet the deepest basins hold moving currents, drifting particles, and animals rather than permanent ice. Cold alone, therefore, cannot explain whether ocean water freezes under miles of crushing pressure. The answer travels from polar winters through sinking currents and finally across the seafloor. At every stage, salt, pressure, circulation, and heat alter the boundary between liquid and solid. The surface may glitter with ice, while denser water escapes beneath its frozen cover. That descending water carries a remembered climate into regions sunlight never directly warms. Its journey creates the deep ocean's coldness, but its chemistry protects continued motion. Direct measurements show gradients rather than a single universal temperature beneath the waves. Mainstream oceanography interprets those gradients through heat exchange, density, and global circulation. No hidden furnace or exotic antifreeze is required to sustain the abyssal liquid. The ordinary physics of seawater becomes extraordinary only because an ocean is immense. Sunlight deposits most of its heat within the upper ocean, especially near the bright surface. As you pass below that heated layer, the available solar energy declines rapidly. In many regions, a thermocline marks the descent, where temperature falls sharply with depth. Below the main thermocline, darkness prevents direct solar heating, and seasonal change becomes muted. Deep water is not simply surface water chilled in place beneath every ocean. Much of it began near high latitudes, where air, ice, and wind removed heat. Cooling increased the water's density, while salinity changes sometimes strengthened or weakened its sinking. In selected polar regions, sufficiently dense water descended and spread into connected basins. This overturning supplies the abyss with cold water formed far from tropical seas. Observations reveal distinct deep water masses with recognizable temperature and salinity combinations. Their properties change gradually as currents mix, encounter topography, and absorb small amounts of heat. Because renewal is slow, abyssal temperatures preserve signals from conditions decades or centuries earlier. Salinity shifts the freezing boundary below the melting point, familiar from pure fresh water. Typical ocean water can remain liquid below 0 degrees Celsius before ordinary sea ice forms. When surface seawater freezes, most dissolved salt is excluded from the growing ice crystals. The rejected brine makes nearby liquid saltier and often denser, encouraging further descent. This process helps connect a frozen polar surface with a liquid global abyss. Pressure adds another influence because the stable freezing temperature changes as depth increases. Within ocean conditions, increasing pressure lowers the freezing point of ordinary ice. Pressure, therefore, does not force the entire abyss into a solid state. Instead, deep temperature must be compared with the local pressure-dependent freezing point. Oceanographers also distinguish measured in situ temperature from potential temperature corrected for compression. That distinction prevents compression-related warming from being mistaken for an external heat source. Shipborne conductivity, temperature, and depth instruments trace the cold structure with fine vertical resolution. These profiles directly observe seawater, but they do not alone reveal every parcel's history. Dissolved tracers provide separate evidence about where deep water formed and how long it traveled. Together, temperature, salinity, and tracers support circulation patterns reproduced by physical models. Models remain interpretations constrained by observations, not photographs of every moving current. The coldest deep water generally occupies pathways connected to powerful polar formation zones. Basins with restricted circulation can be warmer because their deep water renews differently. Seafloor geothermal heat enters from below, but its global average contribution is relatively small. Near hydrothermal systems, localized warming can be dramatic without heating an entire ocean basin. Turbulent mixing transfers heat and salt across layers, slowly modifying water during its passage. Friction and tidal energy help drive that mixing around ridges, slopes, and rough seabeds. No single thermometer can separate these overlapping processes at every depth and season. Repeated sections reveal change, while isolated measurements offer only a moment along a long route. The liquid state persists whenever temperature remains above the relevant freezing boundary. Salt pushes that boundary downward, pressure adjusts it further, and circulation continually rearranges heat. Even water near the threshold usually contains motion and dissolved material that complicate crystal growth. Supercooling can occur locally, although it does not mean the deep ocean is broadly unstable. Ice crystals require suitable thermodynamic conditions, and their formation releases latent heat. That released energy resists further freezing by warming the surrounding water toward equilibrium. At the surface, continued heat loss to cold air can remove that energy efficiently. In the abyss, no comparable atmospheric sink waits directly above each parcel. The seabed usually supplies weak heat rather than extracting enough energy to freeze whole basins. An ice-covered ocean surface also insulates underlying water from the coldest winter air. This insulation slows heat loss even while brine rejection changes the water below. Scientists can calculate freezing conditions accurately, but fine-scale mixing remains difficult to map everywhere. Uncertainty concerns local pathways and rates more than the basic reason seawater stays liquid. The strongest explanation combines observed temperatures with established seawater thermodynamics and circulation. Cold liquid water is therefore not a paradox, but a dynamically maintained planetary condition. That condition governs which organisms can inhabit the largest living space on Earth. Deep animals face slow chemical reactions, scarce food, high pressure, and persistently low temperatures. Their enzymes and membranes function through biochemical adaptations suited to cold, not through internal heating. If you watched a sinking food particle, cold would slow its decay during the descent. That delay can help organic material reach scavengers and microbes far beneath productive surface waters. Many deep fishes conserve energy through low activity, while ambush behaviors, limit costly swimming. A drifting predator detects vibration, approaches selectively, captures prey, and preserves scarce metabolic reserves. Microbes consume falling carbon, alter dissolved chemistry, and return nutrients to deep circulation. Cold temperatures slow many reactions, extending the time carbon can remain below the surface. Overturning eventually brings some deep nutrients upward, supporting new growth in sunlit waters. Thus, polar cooling can influence ecosystems thousands of kilometers from the place. Water sank. Warming at high latitudes may change the density and production of descending water masses. Fresh meltwater can reduce surface salinity, potentially weakening sinking in particular regions. Researchers treat future circulation responses as projections because winds, ice, and buoyancy interact complexly. Observed trends already show that deep ocean properties can shift, although rates differ among basins. Deep waters absorb part of the excess heat accumulating in Earth's climate system. Even tiny deep temperature changes represent enormous energy because the water volume is vast. Continued measurements matter for sea level rise, oxygen distribution, carbon storage, and circulation forecasts. Cold does not make the deep ocean inert. It makes change slow, extensive, and consequential. Future evidence will depend on sustained profiles across seasons, basins, and polar formation regions. Expanded deep observing floats can reveal changes between the widely separated tracks of research ships. Tracer records can test whether renewal pathways accelerate, weaken, or shift geographically. The larger unknown is how rapidly real circulation will carry new surface conditions downward. Models must reproduce past water mass changes before their detailed future pathways earn greater confidence. Under-ice float coverage remains especially valuable where storms, darkness, and moving flows limit access. Better coverage may expose transient cold layers without turning brief anomalies into global conclusions. When you imagine the abyss, picture a slow river of polar history crossing black terrain. Its temperature reflects lost sunlight, distant winter air, mixing, and centuries of motion. Its salt lowers the point where ordered ice crystals can replace flowing water. Its pressure changes that threshold, while compression changes the temperature instruments actually register. Its weak geothermal contact adds heat along the final boundary with rock. The deep ocean remains cold because its waters descend from chilled regions and escape direct sunlight. It remains unfrozen because real seawater stays above its salt and pressure-adjusted freezing threshold. At the opening darkness, the near-icy water keeps moving, carrying Earth's climate instead of becoming stone.